Thank you, Tao, for the introduction, and thanks the organizer for inviting me. NTU and Singapore has a special place in my heart, so I'm always happy to come back. And today, I'm a cybersecurity researcher. So I worked on many different topics. So in the past about 10 years, I've been working on blockchain and the blockchain use in wireless network management, right? So today I want to talk a little bit about DID, verifiable credentials, and particularly our recent work on pseudonym self-provisioning in a vehicular network. So we have seen dramatic technology advancement, right? So the wireless networking, especially wireless technologies, have expanded our connectivity significantly, right? And computing technology also, the advances significantly over the years. So now you can see that the internet is not just connecting computers, it's actually connecting everything, right? So we can see that the cyber world around us, right, are continuously expanding, right? And also it's increasingly intertwined with our physical world, right? So 20 years ago, when we talk about the Internet of Things, we are referring to mostly sensors. And then we're looking at smartphone level of the devices. And now we're looking at autonomous vehicles, right? And you must have heard, year 2025 is the year of the agent. So with AI agent deployed in the network, so there will be a lot of intelligent entities joining us in the cyber world, right? So how do we secure the cyber world, right? So this is a really big question. I think the whole cybersecurity community are working on. But how about the most fundamental questions? How do we make sure who are you, what are you allowed to do, these simple questions in the cyber world, right? So this is fundamentals, right? So the security mechanism like identification, authentication can answer who are you questions, right? So every entity, even in the cyber world, they need a unique ID, and then they need some credentials so that the authentication mechanism can be used to verify their identity, all right? And in the network setting, is typically a challenge response process. I think all of you should know that, right? And then for authorization, access control can basically determine who can use what resources, and also the mechanism access control is basically to enforce this kind of, the use of the resources, like how long you can keep the access, right? So to do that, there's the attributes or claims or roles that need to be defined for those entities, right? So those are the fundamentals, right? Those are all fall into the scope of identity management, right? So the identity management, I think, will be increasingly more important in the cyber world, right? Because the cyber world will be, bigger and more exciting. And so the traditional identity management takes a centralized approach, right? Centralized model. So the users or devices, they will need to receive the ID from a trusted authority, and this trusted authority also issues credentials, and they keep the credentials. And examples like what you are familiar with, Kerberos and 5G, AKA. And the important thing is that the authentication and access control need to be handled by the central server, right? So in order to do access control, you rely on the central server. Federated ID management is a relatively new concept, right? So it allows the multiple organizations using a common identity management, identity providers to help with authentication, right? And authorization. So like a single sign-on. But it's still, the users, they need to register with a trusted identity provider, and the credentials are managed by this central server, and the authentication is done actually by the central server, right? And I think this community, blockchain community, perhaps like this approach, this model best, right? Decentralized identity management, right? So in this decentralized identity management, the users, the devices, the entities, they can create and register their own identifiers, right? Without relying on single central authority. Like they can register their own identities in a public or private blockchain or distributed network, right? And then the credential management, you still need a trusted authority to issue the, or trusted entity to issue you the credentials, right? Verifiable credential. But the authentication, the verification of your credential does not rely on the central server now. You can, the individual can actually verify the credentials. And the access control can also be made decentralized based on the tokens verifiable credentials they get, right? So a very interesting concept here, or cryptographic tools here, are so-called verifiable credential. How many of you know verifiable credential? No? You're blockchain people? All right. So the verifiable credential is a type of, it's a public key-based credential, right? So it's a temporal evident credential that basically contains claims about a subject, right? So for example, this is a credential, somebody's driver's license, but now you have a digital version of that, right? So this contains some claims about the person, and then it's digitally signed by the issuer, right? And the very nice thing about this verifiable credential is also known as an anonymous credential, right? Because it's very much used in privacy preserving technologies. So is that even though this is a signature, right? It's a credential, you can basically prove you satisfy certain properties without disclosure other unnecessary information, right? For example, you have this credential issued by the government. And when you need to basically prove something, if you are a local resident in this zip code, you can show only, you can generate without relying on the third party or the trusted party, a randomized signature, which basically shows you have this property, your zip code is this, but hide the other sensitive or unnecessary information. Of this verifier is only to verify your local residency or something like that, right? So the privacy, this property is known as a selective disclosure, right? So when you when you need to show some property, you can select to show only some of the property and hide the other properties. So this is done by zero knowledge proof, right? And so the very nice property for this anonymous credential is that one anonymous credential can contain a set of attributes, and one user can hold multiple ACs and issued by different issuers. And then this is a very nice property for enable the attribute-based authentication, right? So this is a mimic of the real life credential you have, right? And but it's on the cyber world. All right. So now let's back to the mobile network, right? So I want to talk about a vehicular network, right? So we know the V2X network is part of the 5G, right? Mobile network. So the vehicular network allow vehicles, right, to communicate with other vehicles, to communicate with a roadside unit, to communicate with other infrastructures like traffic light, signs, etc., and with pedestrian people, right? So the vehicular, this is for the mobility, better mobility and safety, right, for the vehicular network. And then there's a basic safety messages, right? So it's broadcast continuously by each vehicle every 100 milliseconds, right? So 1 second, 10 BSM messages. And this message contains a very important mobility information, right? The vehicle ID, location, speed, acceleration, etc. Right? So the secure the V2X communication actually facing some research design challenges, right? So first is those messages, the authenticity of those messages, right? Everybody, I think, other vehicles wants to make sure that these messages are from a legitimate and accountable vehicle, right? So this is already done, right? So they just if every vehicle has a public key, and then they can sign the message, right? So then this is easily done, right? But if a vehicle has a unique ID and a unique certificate, right? And if they keep signing their message like every 100 milliseconds, so you can have the trace of where the vehicle has been, right? So even an observer can actually know where the vehicle they are. So there's a privacy problem, right? So the solution in the current literature is that instead of only carrying one certificate using your unique ID in those messages, right? So the vehicle need to periodically go to a so-called pseudonym certification authority and get the pseudonyms, randomize the pseudonyms. So you have a batch of pseudonyms in your memory, and then you keep changing your pseudonyms, right? When you are sending out those messages. This is the current privacy protection in this network. And of course, when you are using the pseudonyms, then there's accountability issues, right? So those are the research, the tension, right? Design tensions, right? So for the current vehicular PKI, public key infrastructure, so in US, we have SCMS, right? So this is developed by the US DOT. So this is a secure credential management for the US, and the EU has their own CCMS, right? So, but both, the SCMS and CCMS actually use a public key-based, structure, and they have the root CA, then they have the intermediate CA, which take care of different geographical areas, right? And then they use two tiers credential systems, right? So the top tier is there is a long-term enrollment credential. This is your long-term, the credential with your unique ID, and you get from the ECA or EA enrollment, CA or enrollment authority to get the long-term certificate, right? And there's a PCA in both systems. There is a pseudonym CA, right? So you also get the pseudonym certificate from a PCA, right? So for the vehicles running on the road, they have a long-term certificate. They also need to frequently contact the PCA to get the pseudonym for their privacy, right? So this is a current standard. And so I think you all see this is a pseudonym create a huge problem, right? And if you imagine, the US has estimate 350 million vehicles, and if each vehicle need to rotate their pseudonyms, right? You can't use your pseudonym for too long. Let's say every few minutes, 5 minutes, then this is the number of the pseudonym certificates that are required for this vehicular network, right? So if you put this number into perspective, compared to the current largest PKI, which is a web PKI, this is 4 orders magnitude more than the current web PKI, because you want to protect the privacy, right? The main reason is the pseudonym certificates is a huge numbers, because you always need to change, right? And you have to go to the PCA to get that, right? So this leads to the scalability crisis for the vehicular PKI, right? So this is it's a PCA is still a kind of a centralized system, right? You need to go to the PCA to get your pseudonym certificate, and considering the issuing, storing, revoking trillions of the certificates, right? And also the revocation list, right, increases. It's once a vehicle is found, the malicious, and not only revoke that one certificate, you have to revoke all the pseudonym certificate that issued to that vehicle, right? And also, because of the pseudonym, you need to constantly go to the pseudonym certification authority to get your pseudonyms. It requires a vehicle to maintain continuous cellular connectivity. If you lose the network connectivity, you are not going to get your pseudonym certificates, right? So that's all the downsides for this pseudonym, right? Yeah, and also the Sybil attack, right? When you have many, pseudonyms, they are all valid, the certificates, then it's kind of facilitate the Sybil attack, right? So those are all the concerns we need to address. All right. So so for that, we basically propose VPass, which is a new credential scheme for V2X, right? So as I already introduced, so that we actually leverage this decentralized authentication and also the verifiable credential. The goal is that instead of using the traditional public key certificates, which basically clearly state who the ID is in the public key certificate, right? We're using the verifiable credential. So that each vehicle will get their long-term verifiable credential from the ECA and EA. And whenever they need a pseudonym, then they, instead of going to the PCA to obtain a valid pseudonym certificate, vehicle can self-derive their short-term pseudonym. All right. So this will completely remove the need for PCA, right? So the vehicle doesn't have to maintain constant cellular connectivity to get this. And there's a, so we call a window is that the period of time that the pseudonym does not change, right? So it's not for every 100 milliseconds you need a pseudonym, right? So assume the pseudonym can be used for some time, and so we call this is a window. So we also, so the most tricky part is how to design the crypto algorithm to allow all this, those properties, right? So we want to make sure, ensure the vehicle can prove that without reveal their real ID, right? Vehicle can prove they're a legitimate vehicle, and accountability. So if this vehicle is found misbehaving, and authority with the involvement of the tracing authority, then we can de-anonymize this vehicle, hold it accountable, right? We also address the revocation, and as a part of the solution, right? So and also the even itself generated pseudonyms, the pseudonyms remain unlinkable across different windows, right? And then for the this is for the efficiency, right? So we have the crypto zero knowledge proof generation, which is involve very heavy computation in a more powerful ECU, and have the lightweight key operations, and only the hardware attestation stay in the hardware, secure hardware. All right. So this is some details, right? So the entity involved, this is a vehicle, right? And we have the secure element, which is basically the TPM kind of thing. Now the modern vehicle almost all have this automotive HSM, automotive hardware secure module, right? So those are the basically serve as a secure elements, right? So which can be used to store the to carry out the hardware attestation, and then we assume each vehicle will obtain the long-term credential from the EA, right? And in our case, we have this credential stored in the ECU, which is not assumed to be trusted. It's not SE, because SE has limited computing capability, right? SE typically is not, the big enough for the pairing type of heavy computation. So if your algorithm involves pairing, we will realize that outside of the SE. All right. And then those are we have a trusted authority, which is basically to de-anonymize the vehicle once they are found misbehaving. And the other nodes are the nodes who will receive the communication will need to verify the authenticity of the messages. All right. And so the high-level concept for this scheme is that we have two roots of trust, right? We have a hardware trust. So this is it's a hardware automotive hardware security module, which is it's actually available in almost all the modern vehicles, and the hardware SE can do the basically the hardware attestation, right? And the purpose for this, they also keep the the counters that the attackers cannot roll back. So we use this to limit the number of the pseudonyms each vehicle can generate to basically prevent or mitigate the Sybil attack, right? Because Sybil attack is one vehicle will generate many valid pseudonyms. So we are actually using the hardware to rate limit the number of the pseudonyms that one vehicle can generate. All right. And the other root of trust is verifiable credential, right? So this verifiable credential, basically, by definition, it can basically derive the anonymous presentation to show this vehicle is a valid, the credential, right? But in addition to that, we also bind the multiple, the zero knowledge proof in this. We call it a window objects. So it's a one zero knowledge proof, but it proves 4 statements basically. First is it's a valid credential, right? And the ID is one that the user want to hide, right? So the ID is hidden, right? And to enable the de-anonymize of the vehicle, so this ID, actual ID, is encrypted using the TA's public key and is also included in this window objects. And the zero knowledge proof basically shows the encryption, the ciphertext included in this message is encrypted using the same ID, right? I'm not just giving you a random number in the place of this de-anonymization token, right? So the zero knowledge proof will prove that the ciphertext E is indeed encrypted version of MID. And we also have the revocation tag, which is derived from the MID, the identity, right? Identifier. And the zero knowledge proof will also prove that this tag is indeed from the same ID, right? And also the 4th statement is the hardware attestation is also bound to the same authorization context. So they are all on the same ID. So even it's anonymous, but they are based on the kind of the witness, right? Private input is a MID, right? And all this information is bind to this MID using the zero knowledge proof. And we managed to have all this for bind into one zero knowledge proof to be efficient, right? And then once it's done, then the next is the standard broadcast, because the pseudonym we created is in fact the public key for the temporary, the randomness, the private key is a corresponding public key for the ellipse curve encryption, algamma encryption. All right. So, all right. So then this is more details for the design, more crypto designs, right? So this is the enrollment to get to the long-term, the credential, and also the low rate loop is in one window, right? Just we generate pseudonym for just one window. This window can be like maybe 5 minutes or something like that. And so this is the crypto, the construction for to create the zero knowledge proof. And then this is a high rate loop. It's a per beacon, right? You need to send out your BSM messages. And so this is how, the beacon is encrypted, and also at the verifier, how they can basically take 4 steps to verify all this necessary information, right? The message is authenticated using the pseudonyms, right? Because this is by our design, it's a public key of this encryption. And then the hardware attestation, and they are all bind to the same MID, right? So this is the detailed design. And we implemented a small prototype, and we evaluated all the computational cost, because this is a more complex crypto, right? So compared to the traditional, the ECDSA kind of encryption, right? So apparently the most expensive part is the zero knowledge proof, right? So but it's still, the slower, it's still smaller than the 100 milliseconds budget for the every, have 100 millisecond transmission of the message. And yeah, and also if we do not basically use this, the zero knowledge proof for every message, right? So we have a window, right? Window is larger than every packet or every message. So if we compare the bandwidth, verification, storage with the baseline, the current system, what the current system does, because what current system is, you send your certificate, then you sign the message, right? So the bandwidth, right, is a per packet overhead falls below the comparison batch VPKI after 6 beacons. So if your window contains more than 6 beacons, then the bandwidth actually is lower, right? And for the verification, so if your window size is bigger than 63, then your verification cost is actually lower, right? And not to mention the storage, right? So for the storage, then the traditional method, you have to, every card need to keep a large number of the pseudonym certificate, but now you can self-generate, so you don't need that much storage, right? And also now you don't need constantly need the connectivity. All right. So this is basically a new, the credential system that will allow the decentralized authentication, right? And it's not allow decentralized authentication. It's allows the vehicle to self-generate valid pseudonyms to avoid, the getting the pseudonyms from the centralized PCA. All right, and we actually have using the verifiable credential in mobile networks in other contexts, right? So I think this is the first paper we published, after studying the blockchain, the Web3 and verifiable credential. The first paper we published is basically using leverage the anonymous credential systems, implement a UC blocker is basically a block. It's a system that prevents the spam and scam costs, right? So only when the caller basically successfully authenticate themselves anonymously, then they can call you. It's essentially realize add friend operation. So you first need to add friend. So you have the credential, then you can directly call me, right? And yeah, the AAKA is basically realized anonymous authentication protocol for the 5G AKA, so that the mobile users can remain anonymous even to the mobile network operators, right? And so this work did not really use a verifiable credential, but this is a continuation of this work. So when the users access a network anonymously, even the mobile network operators does not know who the user is. How can other people still call you, right? Because the mobility management is based on know who you are and where you are, right? So this is basically the system that can still enable the native calls to an anonymous user. All right. So I think that's all for my talk. And so those are the people that have been involved in this line of research. And thank you.
Okay, thank you very much, Professor Wenjing, for it. This is a very interesting talk and yeah, very useful mechanism. So now we open for 1 or 2 questions, please. Any question? Yes, please. Yeah.
Mhm.
Can you come to the front?
Okay. Be loud.
Thank you. I have only one question: is that if many vehicles are compromised by the same vulnerability, can we pass identify the common cause, or can it only revoke the affected vehicles one by one? Or yeah.
Can you say it again? Can you say your question again?
Yeah, sorry. I mean, if many vehicles are compromised by the same
Many
vulnerability,
parts are compromised.
yeah,
Okay.
can we identify the common cause, or can it only revoke the affected vehicles one by one? Is that
Okay.
Can we do anything to prevent these attacks?
I think the identify the misbehaving vehicle is a separate, the system, even in the standard, right? So if you find this vehicle is misbehaving and you have the track of the messages sent out by this vehicle, and then you can recover its real ID.
I know this, but I mean, the same effect, the same effect can be repeated again and again. Yeah.
We have to treat each vehicle separately because each vehicle, they get their IDs, that they have the different ID, and there's no way for us to de-anonymize the vehicles in a batch manner. So if I identify there were 10 vehicles misbehaving, and then I will basically de-anonymize all these 10 vehicles.
Okay. I see. Thank you.
Yeah. Sorry, I might not understand your question. I'm not sure what do you mean by batch de-anonymization. All right. Okay. Thank you. Any other question, please? Okay, so no question, please. Thank you, Professor Wenjing again, and we presenter. Thank you very much. All right. Thank you.